Tonight, we are going to talk about the fastest humans could ever travel in space. Not with magical warp drives, not through wormholes, and not by breaking the laws of physics, but by asking what might actually be possible if human technology kept advancing for hundreds or even thousands of years. Right now, space feels almost impossible because we are still slow. The moon takes days to reach, Mars takes months, and the nearest stars are so far away that our current spacecraft would need tens of thousands of years to get there. So, if humans ever want to travel beyond the solar system, speed becomes one of the most important questions of all. Could we one day reach 10% the speed of light? Could we go even faster? And if a human ship ever moved close to light speed, would it make the universe easier to cross? Or would speed itself become the danger? Because at extreme speeds, even empty space is not truly empty. A tiny grain of dust could hit like a weapon. Radiation could become deadly, and time on board the ship could begin to separate from time back on Earth. So tonight, the question is simple. What is the fastest humans could ever travel in space? Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the mysteries of the universe, and write in the comments where you are watching from and what time it is where you are right now. It is strange to think that the future of humanity may not depend only on how far we want to go, but on how fast the universe will allow us to move. Tonight, you are watching the Just About Space channel, talking about what is the fastest humans could ever travel in space. To understand that question, we first have to face something uncomfortable. Humans are still very slow in space. That sounds strange, because rockets look fast. A launch feels violent. The engines shake the ground, fire pours from the boosters, and within minutes, a spacecraft can be moving faster than any airplane ever built. From Earth, that looks like speed at its most extreme. It looks like the beginning of freedom from the planet. But space changes the meaning of speed. A speed that feels unbelievable near Earth becomes almost nothing once you compare it with the distances between worlds. A spacecraft can circle Earth in less than 2 hours and still be nowhere near another planet. It can leave Earth behind, cross the distance to the moon in a few days, and still be moving through the smallest neighborhood of the solar system. It can travel for months toward Mars and still only reach the next rocky world. This is the first problem with space travel. We are not slow because rockets are weak in the ordinary sense. We are slow because space is enormous. The scale is what defeats our instincts. On Earth, speed has a human meaning. A car can cross a country, a plane can cross an ocean. A fast train can make a city feel close. Our minds are used to distance being something that machines can shrink. But in space, even the nearest places remain separated by gaps so large that ordinary ideas of travel stop working. The moon is the easiest example. It is our closest major neighbor, the one world humans have already visited, and compared with everything else in space, it is extremely close. And yet the moon is still far enough away that the entire Earth could fit between Earth and the moon many times over. When astronauts traveled there, they were not simply flying upward. They were crossing 250,000 miles of empty space, moving away from every ocean, every city, and every living person behind them. And that is only the moon. Mars is much farther. It is not just a slightly longer trip past the moon. It is a moving target on a different orbit around the sun, sometimes relatively close, sometimes far away on the other side of the solar system. A spacecraft traveling to Mars does not usually fly in a straight line like a car on a road. It follows a carefully planned path around the sun, matching orbits, timing the launch, and arriving months later if everything goes right. That is still inside the inner solar system. Beyond Mars, the distances open wider. Jupiter is not merely the next big planet after the asteroid belt. It is a giant world separated from Earth by a gulf that can take years for spacecraft to cross. Saturn is farther again. Uranus and Neptune are so distant that they begin to feel less like destinations and more like reminders that the solar system itself is a vast structure, not a small collection of planets sitting close together. When a spacecraft reaches the outer planets, it has not reached the edge of space. It has only crossed part of one star's family. That is why human speed is so difficult to judge. Near Earth, orbital velocity is astonishing. Interplanetary probes can move at tens of thousands of miles per hour. Some spacecraft can gain even more speed by falling close to the Sun or using the gravity of planets to change their paths. But even these speeds are tiny compared with the speed of light. And the speed of light is the scale that matters when we talk about the stars. Light can circle Earth many times in a single second. Light from the Sun still takes more than 8 minutes to reach us. Light from the nearest stars takes years. That is the true ruler of space. Not kilometers per hour, not miles per hour. Light years. A light year is not a time in the normal sense. It is a distance. The distance light travels in 1 year. And light is so fast that for human life, it almost feels instant. A beam of light crosses the distance from the Moon to Earth in a little over a second. It crosses the distance from the Sun to Earth in minutes. But between stars, even light needs years. That single fact changes everything. If light itself needs years to travel from the nearest stars to Earth, then a spacecraft moving far slower than light needs much longer. With today's technology, a trip to another star would not be a matter of months or years. It would be a matter of thousands, tens of thousands, or even longer, depending on the speed and destination. The problem is not that we do not know where the stars are. The problem is that reaching them at human speeds is almost impossible. This is why the question of speed becomes so important. Distance is the wall. Speed is the only way to make a doorway. But right now, that doorway is barely open. Humans have become very good at leaving Earth compared with the past. We can place satellites in orbit. We can send robotic missions across the solar system. We have landed machines on Mars, flown past outer planets, and sent probes beyond the main planets into deep space. These are extraordinary achievements, but they also reveal the limit. Our spacecraft can explore our own solar system, slowly, carefully, and with great patience. But the stars remain almost untouched. Even our fastest machines are still crawling by cosmic standards. That sounds harsh, but it is the truth. A spacecraft can be moving faster than any bullet, faster than any jet, faster than anything human beings experience on Earth, and still be moving slowly compared with the distances it must cross. The universe does not care that a speed feels impressive to us. It only cares how long the journey takes. This is why a voyage to the nearest star is so different from a voyage to Mars. Mars is hard, but Mars belongs to the same system. It orbits the same sun. Its distance is enormous, but it is still planetary distance. The nearest stars are separated by interstellar distance. Between the Sun and the next star, there is not a normal road of planets. There is deep space, thin gas, dust, radiation, and years of light travel distance. That gap is the real ocean. The solar system is our island. The nearest stars are other islands so far away that even light takes years to cross the water. And humans are still building boats. This does not mean interstellar travel is impossible forever. It means that if humans ever try to do it, speed must become one of the main problems civilization has to solve. Not speed as a dramatic number on a screen, but speed as survival. Speed as mission duration. Speed as how long a ship must stay alive. Speed as how many generations pass before arrival. Speed as whether the people who launched the mission are still alive when it reaches the destination. A slow interstellar ship is not just inconvenient, it changes the entire meaning of the mission. If a spacecraft takes tens of thousands of years to reach another star, then it is no longer a normal journey. It becomes archaeology in motion. The civilization that launches it may not exist in the same form when it arrives. The language of the builders may change. The people who receive the data, if anyone does, may be unimaginably different from the people who sent it. That is why increasing speed is not only about impatience, it is about connection. The faster a spacecraft can travel, the more the mission remains connected to the civilization that launched it. A trip that takes a few months can still be part of one human story. A trip that takes years can still be understood by one generation. A trip that takes decades becomes harder, but still possible to imagine. A trip that takes centuries or millennia becomes something else entirely. It becomes a message thrown into the future. This is the hidden emotional weight behind the question. What is the fastest humans could ever travel in space? Because the answer decides whether the stars are destinations or only symbols. If humans are forever limited to very small fractions of light speed, then the galaxy may remain physically unreachable for living crews. Robotic probes might go ahead, drifting for ages. Data might return long after the builders are gone. Human expansion beyond the solar system would require generation ships, suspended animation, or technologies we do not yet have. The universe would remain open in theory, but closed in the way human lives experience time. If, somehow, humans could reach a significant fraction of light speed, the picture changes. The nearest stars become difficult, but not completely unreachable. A journey that once took tens of thousands of years might become a matter of decades. Time dilation may begin to matter for the travelers. The ship would still face enormous dangers, but the dream of crossing interstellar space would no longer be only a mathematical idea. It would become a possible future engineering challenge. That is why speed is not a simple technical detail. Speed changes the story. At low speeds, space exploration is mostly about patience. At higher speeds, it becomes about energy. At extreme speeds, it becomes about relativity, shielding, radiation, dust impacts, and the strange fact that moving faster can make the universe more dangerous. The faster the ship goes, the more empty space begins to behave like a hazard. So the problem is not only how fast we can accelerate, it is how fast we can survive. This is one of the most important differences between science fiction and real physics. In stories, faster is usually better. A ship jumps, warps, or accelerates, and distance disappears. But in the real universe, speed has consequences. Accelerating a massive ship requires energy. Stopping it requires energy too. Protecting it at high speed becomes harder. Navigation becomes more demanding. Collisions with tiny particles become more violent. Radiation changes. Time changes. The dream of speed comes with a cost. That cost is why humans are still slow. Not because we lack imagination, and not because we do not want to go farther, but because every increase in speed must be paid for with energy, engineering, protection, and risk. Space does not provide friction like a road or air like the sky, but it also does not give speed for free. To go faster, you must push mass harder. To keep going faster, you need more energy. To carry more fuel, you add more mass. To protect that mass, you add even more mass. The challenge begins to fold back on itself. This is where today's rockets reach their limit. Chemical rockets are powerful enough to lift humans off Earth, which is one of the hardest steps in spaceflight. They can place spacecraft into orbit, send missions to the moon, and launch probes toward other planets. But chemical energy is limited. The fuel can only release so much energy per kilogram. Once a spacecraft is in space, every major change in speed costs propellant, and propellant itself must be carried. That creates a brutal equation. To go faster, you need more fuel, but more fuel makes the spacecraft heavier. A heavier spacecraft needs even more fuel to accelerate. This is why the fastest future of humanity probably cannot be built by simply making today's rockets larger and larger. Chemical rockets open the door to space, but they may not be the technology that carries humans to the stars. They are the beginning of the story, not the final answer. And that is where the next part of the journey begins. If humans are still slow because chemical rockets are limited, then the next question becomes unavoidable. What happens when we move beyond chemical rockets? Before we answer that, we have to understand why chemical rockets are such a powerful beginning, but such a limited future. A chemical rocket is almost the perfect machine for escaping Earth. It carries fuel and oxidizer, burns them together, and throws hot gas downward at incredible speed. It is violent, simple in principle, and strong enough to lift metal, fuel, instruments, cargo, and human beings off the surface of a planet. That is an extraordinary achievement. Chemical rockets are very good at that first step. That is why they deserve respect. Before we move past them, without chemical rockets, there is no space age. There are no astronauts in orbit, no moon landings, no Mars rovers, no deep space probes, no space telescopes. They are not primitive in the careless sense. They are one of the most successful technologies humans have ever built. The problem is that success at leaving Earth does not automatically become success at crossing interstellar space. They can launch from Earth, they can reach orbit, they can send capsules to the moon, they can push robotic probes toward Mars, Jupiter, Saturn, and beyond. Every spacecraft humanity has sent into deep space began with chemical energy doing at least part of the work. Chemical rockets opened the door. But opening the door is not the same as crossing the galaxy. That is the problem. A chemical rocket can be powerful and still be slow on cosmic scales. It can throw a spacecraft into space, but it cannot easily keep increasing speed forever. Once the fuel is burned, the push ends. The spacecraft coasts, corrects its path, and maybe uses gravity assists, but the main energy has already been spent. The problem feeds itself. This is the trap. The rocket must carry the propellant that accelerates it, but that propellant is also part of the mass being accelerated. Add more fuel, and you add more ability to push, but you also add more weight that needs pushing. The result is not a simple straight line where twice as much fuel gives twice as much final speed. The deeper you go into the problem, the more unforgiving it becomes. This is called the tyranny of the rocket equation. The name sounds dramatic, but it fits. The rocket equation describes how much a spacecraft's speed can change based on the speed of its exhaust and the ratio between its full mass and empty mass. In simple terms, if you want more speed from a chemical rocket, you need more propellant. But propellant has weight, and carrying it costs energy. Chemical rockets have another limit too. Their exhaust speed is limited by chemistry. When fuel burns, it releases energy stored in chemical bonds. That energy is real and powerful, but it is not enormous compared with nuclear or relativistic energies. Chemical rockets can reach orbital and interplanetary speeds, but they cannot casually push a large human spacecraft to a meaningful fraction of light speed. That phrase matters, a meaningful fraction of light speed. That is the real divide between solar system travel and star travel. A spacecraft can be amazingly fast by human standards and still move at only a tiny fraction of light speed. If it moves at 1/10,000th the speed of light, the planets may be reachable, but the stars remain almost impossibly far. To make the nearest stars feel like destinations instead of symbols, the speed must rise into a completely different category. Because once we talk about the fastest humans could ever travel, we are no longer asking whether a rocket can reach Mars. We are asking whether a spacecraft can reach speeds that make the nearest stars feel reachable within a human story. 1% of light speed, 10%, even higher. Those numbers are far beyond ordinary chemical propulsion for large crewed ships. This is where the dream of simple interstellar travel begins to break. The rocket must carry the engine must carry the fuel must carry more fuel. And the faster you want to go, the more severe the problem becomes. A chemical rocket is like a match compared with the distance between stars. Bright, hot, powerful for a moment, but not enough to burn across interstellar darkness. And if humans are on board, the problem becomes even harder. A robotic probe can be small. It does not need air, food, water, sleep, or comfort. But a human ship has to carry life. It needs pressure, radiation shielding, thermal control, supplies, recycling systems, medical systems, living space, communication systems, and enough reliability to protect fragile bodies for the entire trip. So chemical rockets become even less suitable for human interstellar travel. They might launch parts of the ship from Earth. They might be used in early stages. But the main deep space propulsion system would probably have to be something else. This is one of the first major turning points in thinking about the fastest humans could ever travel. We realize that launch speed is not the same as travel speed. Escaping Earth is only the beginning. A rocket that can lift humans into orbit has solved one problem, not all problems. It has reached space, but it has not made the stars close. The engine that breaks free from Earth is not necessarily the engine that carries a civilization across interstellar distance. That would change the meaning of a launch. Instead of one rocket leaving Earth for another star, Earth would launch parts, materials, fuel, machines, habitats, and engines over time. The real vehicle would be built where gravity is weaker and where it does not need to push through atmosphere. How do you push something massive fast enough to make interstellar travel meaningful? Chemical energy cannot answer that alone. The reason is not just fuel mass, it is energy density. To reach extremely high speeds, a spacecraft needs enormous energy. The kinetic energy of a moving object increases rapidly as speed rises. Doubling speed does not merely double the energy needed. Chemical fuels simply do not contain enough energy per kilogram to make large, near-light-speed vehicles practical. This is where the universe begins to feel strict. It allows motion, it allows speed, but it demands payment in energy. And the faster you want to go, the more expensive each step becomes. They can take us into space, but they cannot easily take us into the deep future of space travel. They can make us a spacefaring species around Earth, and perhaps across the solar system. But if humans ever become interstellar, they will need something beyond ordinary combustion. That does not make chemical rockets obsolete. It makes them foundational. They are the first stair, not the whole staircase. A future human spacecraft might still begin with chemical rockets lifting components from Earth. It might still use chemical thrusters for docking, emergency maneuvers, or small course corrections. Chemical propulsion is reliable, understandable, and powerful in short bursts. But the main engine for the fastest human travel would need to be more efficient and far more energetic. This is where the next level begins to appear. Nuclear propulsion. Nuclear energy changes the situation because it does not rely on chemical bonds. It taps the energy inside atomic nuclei, where far more energy is stored. A nuclear system could heat propellant more efficiently, produce electricity for long-duration ion drives, or power spacecraft for years in deep space, where sunlight is weak. That step matters, because speed in space often comes from patience. A chemical rocket gives a hard push, then the burn ends. But a more efficient engine could provide thrust over much longer periods, even if the thrust is gentle. Over time, a small continuous acceleration can build into a much larger speed. An engine that keeps working for months or years may eventually create a velocity no short chemical burn could match. This is one of the strange truths of deep space travel. The fastest ship may not be the one with the loudest launch. It may be the one whose engine keeps whispering for the longest time. A nuclear-powered spacecraft could, in theory, do things chemical rockets struggle with. It could push heavier payloads more efficiently. It could reduce travel times to Mars or the outer planets. It could make deep space missions more flexible. It could become a bridge between today's rockets and the more extreme ideas needed for interstellar travel. But even nuclear propulsion has levels. There is nuclear thermal propulsion, where a reactor heats propellant and throws it out of the engine. There is nuclear electric propulsion, where a reactor generates electricity that powers efficient engines, such as ion or plasma thrusters. These systems are not the same. They solve different problems. One offers stronger thrust, another offers efficiency over long periods. Both point beyond chemistry, and both show the direction of the future. To go faster, humans must stop relying only on burning fuel. They must learn to use deeper sources of energy. That is the deeper pattern behind the entire future of speed. The farther we want to go, the more we are forced into more concentrated energy sources. Chemical energy can open the sky. Nuclear energy may open faster travel through the solar system. Fusion and antimatter may belong to the more distant dream of interstellar flight. Each step upward is not just a better engine. It is a deeper way of paying the energy cost demanded by space. That is the quiet transition from the age of rockets to the age of more advanced propulsion. It does not happen because chemical rockets fail. It happens because they succeed at their role and then reveal the next wall. They bring us to space. They teach us how hard space really is. Then they force us to ask what comes after them. Because the fastest humans could ever travel will not be decided by the launch pad alone. It will be decided by what kind of engine can keep pushing after Earth is already far behind. And that brings us to the first real step beyond chemical rockets. Nuclear propulsion. Nuclear propulsion would not mean that the stars suddenly become close. But nuclear propulsion changes the story because it reaches deeper than chemistry. Chemical rockets burn fuel by rearranging atoms and molecules. Nuclear power releases energy from the nucleus itself, where far more energy is stored. That difference matters. It means a spacecraft can use much more energy from a smaller amount of fuel or keep producing power for far longer than a chemical system could. That is why nuclear propulsion feels like the first serious step beyond the rocket age. Not because it solves interstellar travel by itself, but because it begins to loosen the trap. It changes the question from how much fuel can we burn in a few violent minutes to how much energy can we control over the long journey. That is a very different way to think about a spacecraft. A chemical rocket is brilliant at a short, intense escape from Earth. A nuclear spacecraft is more interesting after Earth is already behind it, when the mission needs power, endurance, and the ability to keep working far from the sun. There are two broad ideas that matter most at this stage: nuclear thermal propulsion and nuclear electric propulsion. They sound similar, but they are not the same kind of engine. A nuclear thermal rocket uses a reactor to heat a propellant, often imagined as hydrogen, until it becomes extremely hot. That gas is then expelled out of a nozzle to produce thrust. The basic action still feels familiar. Something hot shoots out the back, and the spacecraft is pushed forward. But instead of burning chemical fuel to create the heat, the reactor provides it. So nuclear propulsion is not only about speed, it is about risk. A faster journey can be a safer journey if the spacecraft can handle the engine, the heat, and the complexity. This matters especially for human missions. A slow trip through deep space is not just boring. It exposes the crew to more radiation, more time in a closed environment, more chances for equipment to fail, and more psychological pressure. If nuclear thermal propulsion could shorten a journey to Mars or make routes through the solar system more flexible, it would not just make space travel faster. It would make some missions more survivable. But nuclear thermal propulsion still has limits. It still needs propellant. It still has mass. The reactor must be safe, controllable, and reliable. The engine must survive extreme temperatures. The spacecraft must protect the crew from radiation. Launch safety becomes a political, technical, and public concern if nuclear material is involved. This is why nuclear propulsion is both promising and difficult. It is not science fiction, but it is not simple. Then, there is nuclear electric propulsion. This is where deep space travel becomes strange again. The most impressive engine may not be the one that produces the biggest burst of force. It may be the one that can keep operating after the launch is forgotten. In deep space, a continuous, gentle push can matter more than a brief, violent one. The spacecraft does not need to fight air resistance, and it does not need to keep an engine running just to avoid falling to the ground. If it can keep pushing, even slowly, velocity can accumulate. This is the quiet power of nuclear electric propulsion. Not a violent launch, a long whisper. A ship pushed by electricity for months, perhaps years, slowly building speed, while the sun becomes smaller behind it. Nuclear propulsion could help humans become faster inside the solar system. That is the key. A civilization that masters nuclear propulsion might begin to see the solar system differently. Mars would still be far away, but not as psychologically distant. The asteroid belt could become more reachable for cargo or robotic work. The moons of Jupiter and Saturn could move from rare scientific targets to places humans can study with heavier, better-powered missions. The outer solar system would still be enormous, but it would no longer feel quite as unreachable. That is a major step, because before humans can seriously think about the stars, they may need to master the solar system. But the question of this video is not only how humans get to Mars faster, it is the fastest humans could ever travel. And here, nuclear propulsion runs into its own wall. Even if nuclear thermal rockets are better than chemical rockets, they still do not easily reach a meaningful fraction of light speed for large human ships. Even if nuclear electric engines can thrust for a long time, their acceleration may be too low for rapid interstellar travel, unless the power levels become enormous. Nuclear fission is powerful, but it is still not the final answer to near light speed travel. It is a bridge, not the destination. Each step gives more energy. Each step also becomes harder to control. That pattern may define the future of fast space travel. The more powerful the fuel, the more dangerous and complicated the technology becomes. Chemical rockets are dangerous, but their principles are well understood. Nuclear reactors are more powerful, but they require shielding, regulation, safety systems, and extreme reliability. Fusion promises even greater potential, but it remains one of the hardest engineering challenges humans have ever attempted. The universe allows higher speeds, but it demands more difficult engines. Nuclear propulsion is the first place where that bargain becomes obvious. A nuclear spacecraft would have to be designed with a different kind of seriousness. The reactor is not just an engine part, it is a power plant in space. It creates heat that must be removed. It produces radiation that must be managed. It may need to operate for years without a repair crew from Earth. It may need to restart, adjust, throttle, and survive vibration, cold, sunlight, darkness, and long periods of isolation. Heat becomes part of the speed problem. So does radiation. This is one of the hidden reasons advanced propulsion is so hard. People often imagine the engine as the only challenge, but the entire spacecraft must be built around the engine's consequences. A powerful engine creates power, but also wastes heat. It offers speed, but also demands shielding. It can make a trip shorter, but it can also make the ship heavier and more complex. The solution to one problem creates new problems around it. Nothing is free. Even nuclear power pays the price. Still, compared with chemical rockets, the possibilities are much wider. A nuclear-powered spacecraft could keep operating after sunlight becomes weak. It could power advanced sensors, electric engines, communication systems, and life support far from Earth. It could move through deep space with a kind of independence that chemical systems struggle to provide. That independence may be the real beginning of deep space civilization. Not just sending lightweight probes on carefully chosen paths, but sending powered machines that can make choices, change course, operate in darkness, and carry enough energy to work far from the sun. The farther humans go, the more power becomes a form of survival. A nuclear ship would carry a piece of controlled stellar-scale energy into the dark. But even then, the stars remain brutally far. A nuclear ship might reduce trips across the solar system. It might make Mars and the outer planets more accessible. It might allow heavier missions, faster transfers, and better power in the dark. But if someone asks whether nuclear propulsion alone lets humans casually fly to the nearest star, the answer is still no. Not casually, not easily, not with anything close to today's engineering. To reach the stars in a human lifetime, a ship must move at speeds that are not just faster than today's spacecraft, but radically faster. 10% the speed of light is already an enormous target. At that speed, the nearest stars become reachable in decades, not tens of thousands of years. But pushing a large human ship to even that speed requires energy far beyond anything chemical rockets can provide, and probably beyond ordinary fission systems in any simple form. This is where nuclear propulsion teaches humility. It is powerful enough to change the solar system, but maybe not powerful enough to conquer the distance between stars. That humility is useful. It keeps the story grounded. Nuclear propulsion is not the answer that lets humans ignore physics. It is the answer that shows how hard the next step really is. If nuclear systems can make the solar system more reachable and still struggle to make the stars close, then the distance to the stars is not just large, it is almost hostile to ordinary engineering. That is why it belongs in the middle of the story. It is the first real step beyond rockets, the first sign that faster human space travel may be possible if we learn to use deeper energy sources. But it also shows that each step upward reveals a larger challenge ahead. Chemical rockets teach us that reaching space is possible. Nuclear propulsion teaches us that moving faster through deep space is possible. But interstellar travel asks for something more. It asks for an engine that can turn the fuel of stars into motion. That is why the next idea feels so powerful. Fusion. Fusion is what powers the sun. It is the process that lights the stars and fills the universe with the energy that makes life possible. If humans could build a spacecraft engine using fusion, then the dream of much faster space travel would move into a new category. Not easy, not guaranteed, but closer to the kind of power that interstellar travel may demand. And that is where the next part of the journey begins. Because if chemical rockets are the first stair, and nuclear propulsion is the first step beyond them, fusion is the moment humans begin to imagine engines that belong not just to planets, but to the stars themselves. That is why fusion feels different from nuclear fission. Fission splits heavy atoms apart and releases energy from the nucleus. Fusion does the opposite. It joins light atoms together and releases energy in the process. This is what powers the sun and every normal star in the night sky. The light falling on Earth, the warmth in our atmosphere, and almost all life on this planet exist because fusion has been burning in the sun for billions of years. So when we talk about fusion engines, we are not talking about a slightly better rocket. We are talking about trying to use a star's method of power as propulsion. Not easy, but imaginable. That is the key difference. Chemical rockets can take us into space, but they do not make the stars feel reachable. Nuclear propulsion can change how we move through the solar system, but it still may not be enough to push large human ships to the speeds needed for star travel. Fusion sits beyond that. It is still incredibly difficult, but it points toward an energy scale that feels closer to interstellar distance. This is why fusion feels like a psychological threshold as much as a technical one. With chemical rockets, the stars feel completely outside human time. With nuclear propulsion, the solar system begins to look more open, but the galaxy still feels locked. With fusion, for the first time, a human-made engine begins to sound like it might belong in the same conversation as the distances between stars. That is where the dream becomes powerful. A ship that accelerates gently for months could reach tremendous speeds. A ship that accelerates for years could reach even more. The idea is not that the crew would be crushed by impossible acceleration. A spacecraft does not need to accelerate at violent levels to become fast if the engine can keep working for a long time. A comfortable acceleration, applied continuously, can become extraordinary over deep time. The passengers may feel only a steady artificial gravity or a gentle push, while the ship slowly builds a velocity no chemical rocket could ever maintain. In the emptiness of space, constant acceleration changes everything. You do not need to be pushed violently all at once. A steady push, if it continues long enough, can build a velocity that seems impossible from the perspective of normal rockets. The ship can become fast through patience, power, and endurance. This is why fusion is often connected to the dream of interstellar travel. If a spacecraft could reach even a few % of the speed of light, the nearest stars would become far less impossible. A journey that might take tens of thousands of years with today's speeds could shrink to centuries or perhaps decades at higher fractions of light speed. That still sounds long, but it changes the meaning of the mission. A fusion ship would need to solve several impossible-looking problems at once. First, it would need controlled fusion. That means creating the conditions where atomic nuclei can merge and release energy, without the system destroying itself and without wasting more energy than it produces. Stars do this with gravity, compressing enormous masses of plasma at their cores. A spacecraft does not have the mass of a star. That is already one of the greatest engineering challenges imaginable. And even if the reaction works, it must work in a controlled way. A star can be enormous, turbulent, and violent because it is held together by its own gravity. A spacecraft cannot allow that kind of chaos. It needs the reaction to happen where engineers want it, when they want it, at the rate they want, without destroying the engine. Fusion for propulsion is not only about creating power, it is about controlling a miniature star-like process inside a machine. That last part matters. A fusion reactor on a planet can be heavy, surrounded by buildings, cooling systems, shielding, maintenance crews, and power infrastructure. A fusion engine on a spacecraft has to fly. Every magnet, shield, radiator, and support structure becomes mass. And mass is always part of the speed problem. A powerful engine that is too heavy may not help enough. Fusion offers hope because the fuel is so energetic, but the machine needed to use that fuel may be extremely complex. This is why fusion spacecraft remain in the realm of future possibility, not current reality. Controlled fusion on Earth is already difficult as a power source. Turning it into a reliable spacecraft engine is another step entirely. It would need to start, stop, throttle, survive radiation damage, operate for long periods, and remain stable far from Earth. A chemical rocket cannot easily pay the energy cost. Ordinary nuclear systems may help across the solar system, but likely struggle with true interstellar speeds for crewed ships. Fusion sits closer to the boundary, where the numbers begin to feel less impossible. It is not magic, but it belongs to the same energy family as the stars. That gives fusion a special place in the story of speed. It is not the final dream, because even fusion has limits. But it is the first propulsion idea that makes a large spacecraft moving at meaningful fractions of light speed feel less absurd. The ship would still be huge, expensive, dangerous, and difficult to build, but the energy source no longer feels completely mismatched with the scale of the mission. That would be one of the great turning points in human exploration. For the first time, humans would not merely be visiting nearby worlds. They would be trying to cross the space between stars within a meaningful span of time. If you want to visit another star system and actually stop there, you need to slow down. A ship moving at a significant fraction of light speed cannot simply arrive and gently park itself. It has enormous kinetic energy. It must spend energy to decelerate, or use some clever method to slow down. If a fusion ship uses half its journey accelerating and the other half slowing down, the mission becomes more realistic, but also more demanding. This is one of the reasons fast interstellar travel is so hard. People often focus on reaching a high top speed, but the full mission requires control. A flyby mission can be simpler, because the spacecraft only has to race past the target and send data as it goes. A crewed mission is different. Humans need to slow down, enter the system, and survive arrival. Without braking, even the most successful flight becomes a blur. The ship could spend decades crossing the distance to another star, only to pass through the system in hours or days, unable to stop and unable to truly explore. For humans, that is not enough. A real interstellar mission would need arrival to be more than a moment. It would need time to study planets, use resources, build shelter, or prepare for another journey. So the fastest useful speed may not be the fastest speed possible. That idea matters for the title of the video. What is the fastest humans could ever travel in space? The answer is not only about maximum velocity. It is about a speed humans can survive, navigate, protect against, and eventually reduce. Speed without control is not travel. It is simply becoming a projectile. In other words, a fusion ship would not be simple just because the fuel is powerful. It would be one of the most complex machines ever built. And the faster it travels, the more the outside environment changes. At a small fraction of light speed, interstellar gas and dust become more serious. At higher fractions, tiny particles hit with devastating energy. The faster the ship goes, the more it must protect its front side. Fusion might provide the speed, but the ship still needs a way to survive moving through space at that speed. That is the paradox of speed. Speed makes distance smaller, but it makes the environment harsher. This means every increase in speed has two faces. One face is hopeful: shorter travel times, closer stars, missions that can fit within human generations. The other face is dangerous: higher impact energies, stronger radiation from the ship's perspective, less time to react, and much greater consequences if anything goes wrong. Fusion offers the hopeful face, but it cannot hide the dangerous one. A slow spacecraft can treat interstellar space as thin and quiet. A fast spacecraft sees that same space transformed into a stream of particles and radiation. It is not flying through a different universe. It is moving through the same universe so quickly that harmless particles become threats. Fusion brings the stars closer, but not gently. It turns the galaxy into something reachable and dangerous. Maybe not easy trips, maybe not comfortable trips, but trips that can be imagined without breaking physics. That is the power of fusion in this story. It does not let humans outrun light. It does not make the universe small. It does not remove the danger of dust, radiation, fuel, heat, or time, but it moves the question from impossible to brutally difficult. There is a huge difference between impossible and brutally difficult. Impossible means the laws of physics close the door. Brutally difficult means the door exists, but opening it may take centuries of science, industry, risk, and patience. Fusion may place interstellar travel in that second category. That is why this chapter of the journey is so important. Fusion does not answer the question completely, but it changes the scale of the answer. It suggests that humans may not be forever trapped at the tiny speeds of present spacecraft. It suggests that if civilization learns to control enough energy, the nearest stars may become difficult destinations instead of impossible dreams. This is why the dream of fusion engines has lasted so long. It sits between reality and imagination. It is grounded in real physics, because stars already use fusion, and humans know the reaction is real. But it remains futuristic, because turning fusion into controlled, practical, lightweight propulsion is far beyond our current spacecraft. Fusion may open the door to high speed, but it does not remove the walls beyond it. That is why the next idea appears in the story. If fusion is the energy of the stars, what comes after it? What fuel could release even more energy from matter? There is one answer that seems almost too extreme to use. Antimatter. Compared with fusion, antimatter feels like the edge of propulsion imagination. Fusion joins nuclei and releases a small fraction of their mass as energy. Antimatter, when it meets normal matter, can convert far more directly into energy. In theory, that makes it one of the most powerful fuels humans can even discuss. And that is where the next part of the journey becomes even more dangerous. Because the more powerful the fuel becomes, the closer speed moves toward possibility. But the closer danger moves with it. That is the truth that appears the moment we talk about antimatter. In principle, this is far more powerful than chemical fuel, and even more direct than fusion. Chemical reactions only use the energy stored in bonds between atoms. Fusion releases a small fraction of mass as energy, but matter-antimatter annihilation can turn much more of the original mass into energy. It seems to offer the thing every starship needs most: energy. A lot of energy. Enough energy, in theory, to push a spacecraft to speeds that chemical rockets could never reach, and that even fusion engines may struggle to approach. If humans ever wanted to move large spacecraft at serious fractions of the speed of light, antimatter would be one of the most tempting ideas on the table. But it is also one of the most dangerous, and one of the hardest. That combination is what makes antimatter so fascinating. It is not a weak idea waiting for better marketing. It is almost too strong. The reason it remains distant is not because the physics is boring, but because the engineering is brutal. The fuel is powerful enough to make people dream about relativistic spacecraft, and dangerous enough that every part of the ship would have to be designed around not letting that power escape in the wrong place. The second problem is storage. You cannot put antimatter in a normal metal tank. If antimatter touches the walls, it annihilates. It does not leak like ordinary fuel. It reacts with the container itself. That means antimatter would have to be held away from normal matter, perhaps using electromagnetic fields or some other containment method far beyond ordinary fuel storage. That is not a small engineering problem. It is the central danger. A chemical fuel tank can rupture and explode, which is already terrifying. A nuclear system can fail in dangerous ways. But antimatter containment failure would be in a different category. A large enough quantity would not be fuel anymore. It would be a disaster waiting inside the vehicle. This means antimatter is not the kind of fuel a civilization would use casually. It would require a level of precision and infrastructure that makes present-day spaceflight look simple. The containment system would be as important as the engine. The storage system would be as important as the fuel. The ship would not merely carry antimatter. It would spend the entire mission preventing the antimatter from becoming something else. The fuel would be a source of speed and a permanent threat. But if it worked, the potential would be extraordinary. This is why the idea refuses to disappear. Even after every warning, the energy is still there. A fuel with that much energy density changes what can be imagined. A future civilization with enough industrial power might look at antimatter not as fantasy, but as one of the few ways to push large payloads towards speeds where time dilation, interstellar travel, and nearby star systems become part of practical planning. An antimatter-powered spacecraft might use annihilation energy to heat propellant, generate electricity, or directly create high-speed exhaust from the reaction products. Different concepts exist in theory, but they all face the same broad challenge: how to turn an incredibly energetic reaction into controlled thrust. Releasing energy is not enough. An engine must direct it. That difference matters. To accelerate a spacecraft, the energy must be turned into something leaving the ship in one direction, so the ship moves in the other. With antimatter, this is difficult because the reaction products can include extremely energetic particles and radiation. Some of that energy may be hard to direct. Some may become dangerous heat. Some may require heavy shielding. Again, the engine is not just the fuel. The engine is the entire system needed to control what the fuel does. Every answer adds machinery. Machinery adds mass. Mass makes acceleration harder. Once again, the same pattern returns. The universe offers a way forward, but it demands payment in engineering. That payment would be paid in every direction. The engine needs control systems. The control systems need power. The storage needs fields. The fields need generators. The generators need cooling. The cooling systems need radiators. The radiators need structure. The structure needs protection. By the time the fuel is ready to push the ship has become a chain of compromises. Still, the reason antimatter remains so important is that it sits near the top of realistic energy density. If humans ever wanted to build a very fast crewed spacecraft, one moving at a large fraction of light speed, antimatter might become one of the few options that does not immediately collapse under the energy requirement. As a physical concept, it shows how far propulsion might go before reaching the ultimate barrier: the speed of light. Antimatter would not let humans break that barrier. Nothing with mass can simply accelerate to light speed under known physics. As a spacecraft gets closer and closer to light speed, the energy required rises more and more. Light speed is not just a very hard speed to reach, it is a boundary for massive objects. But antimatter might allow speeds that feel almost impossible from today's perspective. Not light speed, but perhaps a significant fraction of it, in the most extreme future concepts. That is where the title of the video becomes more intense. The fastest humans could ever travel may not be limited by whether energy exists in principle. It may be limited by whether humans can control the energy without destroying the ship, killing the crew, or making the mission too massive to accelerate. With antimatter, the problem becomes less about imagination and more about survivability. That may be the most important sentence in this part of the journey. Antimatter is easy to imagine in a simple drawing: a futuristic engine, a glowing exhaust, a ship racing toward the stars. But the real question is not whether a drawing can look fast. The real question is whether a machine can hold the fuel, direct the energy, protect the crew, and keep doing all of that for the entire mission. Because even if the engine works, the outside universe becomes more dangerous as velocity increases. At 10% light speed, interstellar dust is already a serious threat. At higher fractions, the ship is moving through gas and particles with terrifying energy. Tiny grains become projectiles. The faster the ship moves, the more the empty space ahead behaves like a storm. Antimatter may give the ship speed, but speed turns the universe into a hazard. At low speed, the space between stars is thin and quiet. At high speed, that same space begins to behave differently from the ship's point of view. The ship is not only moving through the universe, it is turning every particle ahead into an incoming event. The faster the ship goes, the more violent those events become. A fuel that solves acceleration does not solve impact. That protection adds mass. The mass requires more energy. More energy requires more fuel. More fuel requires more containment. More containment adds more mass again. It would not be a fantasy starship. It would be a controlled disaster that must never lose control. So the question becomes not simply how fast antimatter can push a ship, it becomes how fast antimatter can push a ship that can also stop. Stopping is the part that often ruins the fantasy. A spacecraft at extreme speed has not only gone far, it carries enormous kinetic energy. That energy must be dealt with before arrival can become exploration. If the ship cannot slow down, then the destination becomes a flash outside the window. Not a new home, not a research base, not a place where humans can actually do anything. For humans, the challenge grows brutally. Every extra person increases mass. Every extra year of travel increases the need for support systems. Every shield protects the crew, but slows the ship. Every safety system makes the mission more survivable, but harder to accelerate. Antimatter may be powerful enough to make high speed possible, but the human body brings requirements that energy alone cannot erase. Air is mass, water is mass, food is mass, radiation shielding is mass, living space is mass, medical equipment is mass, redundancy is mass. The faster the ship must go, the more every kilogram matters. So antimatter does not make human star travel easy. It makes the hardest version of it slightly more physically imaginable. That is still a huge shift. Human history often moves through ideas that begin this way. Not easy, not practical yet, but no longer forbidden by the basic rules. Antimatter belongs to that category. It does not promise that humanity will build starships. It only says that matter itself contains enough energy to make the dream less absurd, if a civilization can ever control it. That is still important. The difference between impossible and physically imaginable is enormous. Antimatter tells us that nature contains enough energy in matter to push spacecraft to extreme speeds, at least in principle. But it also shows that having energy is not the same as having a mission. To make antimatter useful, humans would need a civilization capable of producing it, storing it, protecting it, directing it, and building spacecraft around it. And even then, it would not give humans the whole galaxy. A ship, traveling at a fraction of light speed, still needs years to reach nearby stars and far longer to cross large parts of the Milky Way. Time dilation may help the travelers at very high speeds, but it does not make the outside universe stop aging. Speed solves distance only partially. It creates new kinds of separation. This is why antimatter feels like a warning. It warns us that the fastest path is not always the safest path. The most energetic fuel creates the most severe responsibilities. A civilization that can use antimatter would be powerful, but also forced to become careful. The same technology that could push a spacecraft toward another star would demand perfect control, deep redundancy, and a constant respect for failure. Yes, the energy exists. Yes, the physics allows enormous speeds below light speed. Antimatter is not the easy answer. It is the extreme answer, and extreme answers come with extreme dangers. That is why the story cannot stop here. If the problem is carrying fuel, storing fuel, shielding fuel, and accelerating all that mass, then there is another way to think about speed. What if the fastest spacecraft does not carry its main energy source at all? What if the power stays behind and the ship is pushed from far away? That idea changes the shape of the problem. Instead of building a giant crewed spacecraft filled with dangerous fuel, you build something small and light. Instead of carrying all the energy on board, you fire energy at it from a distance. Instead of a massive engine, you use a sail. Not a sail pushed by wind, but by light. This is where the next possibility begins. Laser sails, tiny spacecraft pushed by enormous beams of light. perhaps fast enough to reach a significant fraction of light speed. Not because they carry the most powerful fuel, but because they barely carry fuel at all. That is what makes laser sails such a different idea. Laser sails change the question. What if the energy does not ride on the spacecraft? What if the power stays behind? This is the basic dream of laser sail propulsion. Not a rocket throwing fuel backward. Not a reactor heating propellant. Not antimatter annihilating inside a dangerous engine. Just light pushing a sail. The simplicity is what makes the idea so powerful. It attacks one of the oldest problems in rocketry. The spacecraft normally has to carry the fuel that gives it speed. With a laser sail, the ship does not need to carry the main energy source. The power system can be huge, heavy, and complicated because it stays behind. The thing being accelerated can be almost impossibly light. At first, it sounds too gentle to matter. Sunlight pushes on objects all the time, but the force is extremely small. A person does not feel sunlight pushing them across the ground. But in space, if the sail is very light and the beam is powerful enough, even a tiny force can become important. The key is not just the force, it is the mass being pushed. A giant human ship is heavy. A tiny probe can be extremely light. That difference may decide which objects reach the highest speeds first. A human ship must carry a small world. A tiny probe only has to carry a purpose. It can be reduced to the minimum. Instruments, electronics, communication, and structure. The less it carries, the more the beam can do. In that sense, laser sails do not win by being the strongest engine. They win by refusing to bring an engine at all. This is why laser sails are often connected to tiny spacecraft, not human starships. They may be one of the best ways to send something to another star very fast. But that something may not be a crew. It may be a machine, not a person, not a colony ship, not a giant spacecraft, but a messenger. This is the opposite of the antimatter problem. With antimatter, the ship carries immense energy on board and must survive the danger of that fuel. With laser sails, the spacecraft carries almost no fuel, but it depends on a gigantic power system somewhere else. This is not like shining a flashlight at a wall. It is more like trying to push a feather with light across the solar system and aim it toward another star. The aiming problem would be one of the most difficult parts of the mission. The probe would not simply sit still while the beam pushes it. It would accelerate away, becoming harder to track and harder to keep inside the beam. The laser ray would need to hold alignment with incredible precision. The sail would need to remain stable, because even a small tilt could send the probe off course. A laser sail sounds simple only until you imagine the details. The beam must be powerful, the sail must be light, the material must survive, the aiming must be precise, the probe must remain stable. And after all of that, the mission has only begun. The acceleration phase could be short compared with the full journey, but it would be the most intense part of the launch. The sail would be bathed in concentrated light. If it absorbs too much energy, it heats. If it heats too much, it deforms or fails. If it deforms, it may lose alignment. A mission that depends on light pressure also depends on materials that can survive being pushed by light without being destroyed by it. Even a tiny grain of dust can matter. That is the recurring lesson. Every way of going faster creates a new way to fail. Laser sails avoid carrying fuel, but they do not avoid the universe. They still have to move through interstellar space. They still have to survive the speed they achieve. This is where the idea becomes less clean and more real. A tiny probe, moving at a large fraction of light speed, has very little time to respond to hazards. It cannot dodge every dust grain. It cannot carry a massive shield. It may have to trust probability, design, and small protective layers. The fastest path may also be the path where the spacecraft is most exposed. A few images, a few measurements, a faint message from another star. And yet, that would be historic. But this video is asking about the fastest humans could ever travel, and that creates a problem. Laser sails are exciting because they may be fast, but they are not obviously useful for humans. The human body changes the entire design. People cannot be reduced to a chip and a sail. They need pressure, temperature, air, water, food, radiation protection, waste recycling, medical systems, and space to live. They also need acceleration low enough to survive for the required time. A beam that can throw a tiny probe violently forward may not be usable in the same way for a crewed vessel. The scale becomes extreme very quickly. A small probe can be accelerated like a seed. A human ship is more like a city. Pushing a city with light is not impossible in the purest physical sense, but it is far beyond the simple version of the idea. And then, again, comes braking. Braking is the shadow behind every fast mission. It is easy to imagine a laser pushing something away from the solar system, but harder to imagine another beam waiting at the destination. Unless a civilization has already built infrastructure around another star, the arriving spacecraft may have no external power source to help it slow down. That means the mission must either accept a flyby, carry its own braking system, or use a more complicated method that has not yet been proven. A crewed ship has to stop. This is one of the biggest weaknesses of laser sails for human travel. They are better at acceleration from home than deceleration at the destination. So laser sails reveal a strange possibility. The fastest human-made objects may not carry humans. They may be tiny probes. Humans are not tiny probes. Humans bring mass, fragility, and needs. This is where the story becomes more honest. The future of speed may split into two paths. On one path, small robotic probes travel first, extremely fast, perhaps at a large fraction of light speed, crossing to nearby stars and sending back faint data. On the other path, human ships move much more slowly because they must carry life and survive arrival. That split may define the early interstellar age. Machines could become the scouts, racing ahead at speeds too harsh for people. Human missions, if they ever follow, may be larger, slower, better protected, and more careful. The first object to reach another star quickly may not carry a voice, a face, or a person looking out of a window. It may carry only a camera and the memory of the civilization that launched it. They would be fast because they are small. They would be small because speed demands sacrifice. That is the deeper lesson of laser propulsion. Speed may require giving things up. Give up the engine and the ship becomes lighter. Give up the fuel and the ship becomes faster. Give up the crew and the mission becomes easier to accelerate. Give up stopping and the mission can go faster still. Each sacrifice makes speed more possible, but also makes the journey less like human exploration. A tiny flyby probe at 20% light speed is a triumph of engineering, but it is not humans walking under another star. It is a message passing through. That is beautiful, and also lonely. A laser sail probe might spend decades crossing the void, then have only a brief encounter with another star system. It might pass planets at unimaginable speed, unable to slow, unable to turn back, unable to enter orbit. Its entire mission might depend on minutes or hours of observation after years of travel. That is not a journey in the human sense. It is a thrown instrument. But sometimes thrown instruments are how exploration begins. But there is another difficulty. So even though the probe is simple, the system is not. Laser sail propulsion shifts complexity away from the spacecraft and into the civilization that launches it. That civilization would need to build the beam, power it, aim it, cool it, and protect everything around it. The laser array might be larger than cities. It might need to operate in space, It might demand energy systems on a scale that only a very advanced spacefaring society could provide. The spacecraft is tiny, but the launch system is enormous. The probe is light because the civilization behind it is heavy. But for humans, the challenge remains severe. That is why laser sails give us a surprising answer. The fastest practical spacecraft may be the least human-looking. No corridors, no windows, no crew, no engine room. Just a tiny machine and a shining sail, pushed by a beam from home. It is a humbling answer. We imagine the future of space travel as giant ships carrying crews into the unknown. But the first truly fast interstellar travelers may be smaller than a suitcase, perhaps smaller than a human hand in their core electronics. The fastest thing we send may not look like a ship at all. It may look like a fragile piece of technology attached to a reflective sheet. This pushes the story toward the next question. If tiny probes can go very fast, could humans ever do the same? Could a crewed ship ever travel at 10% light speed? 20%? More? Could people survive the acceleration, the dust, the radiation, the time dilation, and the need to slow down? Or will the fastest speeds always belong to machines too small and too fragile to carry us? That is where the real human limit begins. Because speed itself may be possible, but carrying humans at that speed is another problem entirely. The next step is to ask not what a tiny probe can survive, but what a human body inside a real spacecraft could ever endure. This is where the question becomes much harder. Humans are different. A human spacecraft is not just a machine that moves through space. It is a small environment built around fragile biology. It must protect soft bodies from acceleration, radiation, vacuum, isolation, heat, cold, failure, and time. So the fastest humans could ever travel is not simply the fastest speed a spacecraft could reach. It is the fastest speed a spacecraft could reach while still keeping people alive. That is a completely different question. It means the human speed limit is not printed on a speedometer. It is hidden in the relationship between engine power, ship mass, crew survival, shielding, braking, and mission length. A future civilization might build a machine that can move faster than any human ship could safely move. But if the machine cannot carry people, protect them, and bring them somewhere useful, then it does not answer the human version of the question. Speed alone does not crush you. If you are inside a spacecraft moving at a constant speed through empty space, you may not feel the speed at all. What the body feels is acceleration, the change in speed or direction. That is why a crewed spacecraft cannot simply jump from rest to 10% of light speed. It must build speed over time. This may seem like a small detail, but it changes the whole picture. A tiny probe can be accelerated more aggressively because it has no body to injure. A human ship has to treat acceleration as part of the living environment. Too much force for too long becomes dangerous. Too little force means the ship takes longer to reach its target speed. The fastest human journey must fit between those two pressures. If a spacecraft accelerated at 1 g, the crew could feel a steady downward force similar to standing on Earth. The ship would push them forward and the floor would push back, creating a kind of artificial gravity. Inside the ship, life might feel strangely normal while the spacecraft steadily gained speed. A constant 1 g acceleration is powerful over long periods, but it still requires the engine to push the entire ship continuously. The spacecraft must supply enormous energy for every second of that acceleration. It must keep its engine stable, remove waste heat, carry fuel or receive energy from somewhere else, and protect the crew while becoming faster and faster. That is why a 1 g starship sounds simple only from the inside. To the crew, it might feel like standing on a floor. To the engine, it is a vast demand that never stops. Every second, the ship must push not only the people, but the habitat, shielding, tanks, radiators, computers, structure, and whatever fuel remains. The comfortable experience for the crew may be an extreme engineering burden for the vehicle. The human body might tolerate the acceleration. The spacecraft might not tolerate the energy demand. This is one of the most important divides in near-light-speed travel. The biology is not always the first limit. Humans can imagine living under steady acceleration if it is gentle enough. The real challenge is building an engine that can keep pushing a large, shielded, life-supporting spacecraft long enough to reach extreme speed. And then, after all of that, the ship must slow down. That means a realistic crewed mission might accelerate for part of the journey, coast for part of the journey, and decelerate for the final part. Or it might accelerate for the first half and decelerate for the second half. Either way, the useful speed is the one that still allows arrival. For humans, that changes everything. A speed like this does not make the nearest stars easy, but it makes them thinkable. It turns the journey from something that outlives entire civilizations into something that might fit inside the memory of one crew or one mission program. That is why the first serious human interstellar ship would not need to approach light speed itself to be revolutionary. Even a small fraction of light speed would be a break from all previous space travel. That is why 10% of light speed may be one of the first truly meaningful targets for crewed interstellar travel. Not because it is easy, but because it is the first speed that begins to make nearby stars feel connected to a human lifetime. At that speed, the ship is still slow compared with light, but unbelievably fast compared with anything humans have built for crewed travel. The stars would not rush past like streaks from a science fiction film. The journey would still be long, quiet, and mostly empty, but the destination would no longer feel like a myth. The crew could leave with the real expectation that the mission might reach another stellar neighborhood within a meaningful span of time. And 10% is still far below light speed. There is a huge difference between 10%, 50%, 90%, and 99% of light speed. To human imagination, all of these may sound like almost light speed, but physics treats them very differently. The closer a massive spacecraft gets to light speed, the more energy is required for each additional increase. Going from 0 to 10% of light speed is already extraordinary. Going from 10% to 50% is far harder. Going from 50% to 90% is harder again. And going from 90% to 99% becomes almost a different universe of difficulty. This is because light speed is not just a fast number, it is a limit built into space-time. A spacecraft with mass cannot reach it by ordinary acceleration. You can get closer and closer in theory, but the cost grows without end as you approach the limit. So the fastest humans could ever travel is not likely to be exactly light speed. It would be some fraction below it. The real debate is how large that fraction could ever become. Could humans reach 10%? Perhaps. In a very advanced future, with fusion, antimatter, beamed propulsion, or technologies that combine several ideas. Could humans reach 50%? That becomes far more extreme. The ship would need staggering energy, intense shielding, and extraordinary braking ability. Could humans reach 90%? Under known physics, it may not be impossible in the abstract, but for a large crewed spacecraft, it becomes almost unimaginable. The limit is not only physics, it is engineering, it is energy, it is survival, and it is purpose. A civilization does not only ask, can we reach this speed? It must ask, why choose this speed? A faster ship costs more, risks more, and suffers harsher impacts from the environment. If a slower speed can reach the destination safely within a useful time, then pushing closer to light speed may not be worth the danger. This is where human space travel becomes different from a race. In a race, the winner is the fastest. In interstellar travel, the winner is the ship that arrives with its crew alive, its systems working, and its mission still possible. Speed is only valuable if it remains under control. Control includes more than steering. It includes knowing how to handle the ship's energy, how to protect its forward face, how to keep the crew alive if a system fails, and how to reduce speed before arrival. A starship moving at a major fraction of light speed is not something that can be casually corrected at the last moment. Its motion has to be planned with extraordinary precision, long before it reaches the target. That is why the human limit may be much lower than the machine limit. Tiny probes can be accelerated harder. They can accept flyby missions. They can be built in large numbers with the knowledge that some may fail. Humans cannot be treated that way. A crewed mission demands caution, redundancy, mass, and systems that keep working through years of deep space. Every safety layer lowers the possible speed. But without those layers, the speed becomes meaningless. This is why crewed starships may look heavy and unglamorous compared with fast probes. They may need thick forward shielding, redundant life support systems, spare parts, repair robots, radiation shelters, and large reserves of power. All of this makes the ship slower, but it also makes the mission real. The fastest possible object is not always the fastest possible home. And then there is the human mind. This makes the fastest human journey partly a social problem. A crew traveling for years or decades cannot live as if they are on a short mission. Their spacecraft must support human behavior, not just human biology. People need structure, roles, privacy, trust, and a reason to believe the sacrifice makes sense. If the ship is a closed world moving through interstellar darkness, then its internal society becomes part of the propulsion problem, because a mission can fail even if the engine keeps working. Still, the dream remains powerful. There is something deeply human about wanting to cross the gap anyway. The distances are unreasonable. The energy is enormous. The risks are severe. And yet, the idea remains compelling, because speed is the difference between seeing the stars as lights in the sky and seeing them as places. A fast enough human ship would not make the universe small, but it would make the nearest pieces of it reachable in a new way. Once the ship is moving that fast, every decision matters. Turning around is not simple. Stopping is not simple. Avoiding hazards is not simple. Even changing the path slightly requires planning. The crew is riding inside a massive amount of kinetic energy, and that energy cannot be ignored. That fact alone makes it dangerous. So could humans ever travel close to light speed? The honest answer is complicated. Humans could probably not reach light speed itself. Under known physics, that boundary remains closed to massive objects. But humans might one day travel at meaningful fractions of light speed if civilization becomes advanced enough, patient enough, and willing to build machines far beyond anything we can create today. 10% of light speed may be the first imaginable target for serious crewed interstellar travel. Higher speeds may be possible in theory, but each step upward becomes more difficult and dangerous. For humans, the fastest useful speed may be somewhere below the speeds our most ambitious probes could reach. The future may send small machines first, then slower crewed ships later. And only after centuries of development might humans approach the deeper relativistic speeds that make time itself begin to separate dramatically between the ship and Earth. And that is the next strange truth. At extreme speed, the question changes again. It is no longer only how fast the ship is moving, it becomes how time passes for the people on board, compared with everyone left behind. Because once a human spacecraft moves close enough to light speed, speed does not only change distance, it changes time. This is one of the strangest truths in all of fast space travel, because it does not match the way time feels in ordinary life. On Earth, time seems universal. 1 hour for you feels like 1 hour for everyone else. We live as if the whole universe is moving through one shared present moment. And for daily life, that illusion works well enough. But the universe is not that simple. At extreme speeds, time depends on motion. A clock moving very fast compared with another clock does not tick at the same rate from that outside point of view. This effect is called time dilation. It is part of relativity, and it becomes more important the closer something moves to the speed of light. At ordinary human speeds, the effect is tiny. At interstellar speeds, it can become one of the most important parts of the journey. For the crew on board the ship, time would feel normal. That is the first thing to understand. The people inside the spacecraft would not look around and feel their watches turning into science fiction. Their hearts would beat normally. Meals, sleep, conversations, repairs, and routines would all happen in the ordinary rhythm of life on board. A minute inside the ship would still feel like a minute. But compared with Earth, that year may not match. That mismatch is not caused by the ship's clock being broken. It is not a mechanical problem or a trick of perception. It is the structure of the universe itself. Two clocks can both be working perfectly and still disagree after one of them has traveled at enormous speed. The difference is not inside the clock. The difference is in the path through space-time. From Earth's point of view, a ship moving close to light speed would have a clock that appears to run more slowly. The faster the ship moves, the stronger the effect becomes. At 10% of light speed, time dilation exists, but it is not dramatic. At half the speed of light, the difference becomes more noticeable. At 90%, it becomes much stronger. This changes the meaning of travel. A fast enough spacecraft does not only cross space, it separates its passengers from the time of the world they left behind. That is why near-light speed travel feels powerful and sad at the same time. It offers a way for travelers to experience a shorter journey than Earth would measure. A trip that takes decades for people waiting at home might feel shorter for the crew if the ship moves fast enough. In a sense, speed can help the travelers survive long distances by reducing the time they personally experience. But there is a cost. The people left behind continue aging. Earth continues changing. Civilizations continue moving forward. If the ship returns after a high-speed journey, the crew may come back to a future that feels far beyond the time they lived through. They may have experienced years or decades, while Earth experienced much more. This is not time travel in the fantasy sense, because the crew cannot go back. They are following a path through space-time, where less time passes for them than for those who stayed behind. They can move into Earth's future, but not back to its past. That is what makes this so different from ordinary exploration. A ship sailing across an ocean can return to the same society, the same language, the same family, only older by the length of the voyage. A relativistic starship may return to a world that has moved beyond the crew's entire historical moment. The journey becomes not just travel through space, but a one-way drift away from the present. Speed becomes a kind of separation deeper than distance. Distance separates places. Relativistic speed separates lives. With relativistic travel, the psychological gap becomes stranger. The crew lives through ship time. Earth lives through Earth time. Each side measures the mission differently. The farther and faster the mission becomes, the harder it is to call it a normal conversation. But this does not make the journey easy. It does not reduce the energy required to reach that speed. It does not remove the need for shielding. It does not solve braking. It does not protect the ship from dust, radiation, or failure. Time dilation helps the travelers experience less time, but it does not make the universe safe. In fact, the speeds needed for strong time dilation are exactly the speeds where danger becomes extreme. To feel a dramatic difference in time, a ship must move at a large fraction of light speed. So time dilation is not a shortcut. It is a consequence. it comes with the same speed that creates the other problems. This is an important distinction. Time dilation can make the trip feel shorter for the crew, but it does not make the distance physically disappear for the rest of the universe. Earth still sees the ship take the outside travel time. The destination still waits across real light years. The engine still has to push the mass. The shield still has to face the particles ahead. Relativity changes the crew's experience of the journey, not the price of building the journey. Even if the ship returns, it does not truly return to the same world. It returns to a later one. The faster humans go, the more time itself becomes part of the price. Space and time are not separate backgrounds. They are connected. When a spacecraft moves extremely fast through space, its relationship with time changes. The speed of light remains the same for everyone, and the universe adjusts space and time around that rule. This is why light speed is not just another speed. It is woven into the structure of reality. That is also why light speed feels so absolute. It is not like a speed limit sign on a road that a stronger engine might ignore. It is part of the rulebook that connects space, time, energy, and causality. A massive ship can approach it, getting closer and closer in theory. But the closer it gets, the more extreme the cost becomes. The universe does not forbid speed gently. It makes the final steps more and more demanding. But reaching those higher speeds is exactly where the engineering becomes brutal. This is the trap again. At modest fractions of light speed, time dilation may not be strong enough to transform the mission emotionally. At extreme fractions, it may transform the mission deeply. But the spacecraft must become almost unimaginably capable. The zone where relativity becomes useful is also the zone where propulsion, shielding, navigation, heat management, and braking all become more severe. The speed that makes time dilation useful is also the speed that becomes hardest to reach and hardest to survive. A ship cannot simply choose 90% of light speed because the time dilation sounds helpful. It must pay the energy cost, protect itself from the environment, and eventually slow down. The more time dilation helps the crew, the more extreme the mission becomes. That is why relativistic travel is not just transportation. It is exile from the present. The crew would carry a version of Earth inside their memories, but that version would not wait for them. Their ship might preserve their bodies and their onboard time, yet it could not preserve the outside world. This makes relativistic travel both hopeful and tragic. It gives humans a way to reach farther, but only by letting the rest of history run ahead. That is the strange bargain of relativity. Speed gives the crew more reachable distance, but it takes away shared time. For a civilization, that bargain would be difficult to accept. A faster ship might be celebrated as a triumph, but for the people on board, it could also mean saying goodbye to everyone in a deeper way than any normal journey requires. The mission would not only need engineers and pilots, it would need people willing to become temporarily separated from home. Again, the same theme returns. At extreme speeds, nothing stays simple. Distance changes, time changes, light changes, danger changes, and the human meaning of the journey changes with them. This is why the fastest possible speed may not be the most useful speed. A mission planner might choose a slower journey to keep the crew more connected with Earth, reduce engineering risk, or make braking easier. Another mission might accept a stronger time shift because the destination is farther away. The correct speed would depend not only on what physics allows, but on what the mission is willing to lose. So the fastest humans could ever travel may come with a choice: stay slower and remain more connected to Earth, go faster and reach farther while Earth slips into the future. That is a haunting thought. The fastest route may not be the most human one. Because near light speed, the ship does not just cross the universe, it leaves the present behind. And once the present is left behind, There is no engine that can bring it back. The ship can slow down. It can turn around. It can return to the solar system. But it cannot return to the exact time it departed from. The crew may survive the journey, but the clock of the universe outside the ship has still moved on. And yet, even this is not the final danger of going fast. Time dilation may be strange, but it does not tear the ship apart by itself. The crew may survive the altered time. They may accept the future shock. They may understand that Earth will age differently. But the ship still has to move through real space at an extreme velocity. It still has to face dust, gas, radiation, and microscopic particles that become more dangerous the faster the ship travels. The next truth is more physical, more immediate, and more violent. At some point, going faster does not only change time, it turns empty space into something that can kill you. That is the next truth of extreme space travel. Space looks empty because, compared with Earth, it almost is. There are no oceans, no mountains, no roads, and no thick atmosphere in front of the ship. A spacecraft can coast through darkness for years and appear to be moving through nothing. But at high enough speed, almost nothing is still enough to become dangerous. The danger is not that interstellar space is secretly crowded. The danger is that speed changes the meaning of every particle. At low speeds, a tiny grain of dust may be only a small engineering problem. At ordinary spacecraft speeds, micrometeoroids are already taken seriously, but shields can be designed around them. As the ship moves faster and faster, each collision becomes more violent. The grain has not changed, the ship has. A piece of dust that seems meaningless while floating in space can become a weapon when the spacecraft meets it at a fraction of light speed. At 10% of light speed, the front of a spacecraft is no longer simply a nose or a hull. It is a shield facing a storm. Not a storm made of wind and rain, but a storm created by the ship's own motion through the thin material between stars. Interstellar space contains gas, dust, charged particles, and radiation. It is extremely thin, but it is not perfectly empty. When the ship is slow, that material barely matters. When the ship is fast, the spacecraft runs into it with enormous energy. This is the strange reversal. The faster the ship goes, the less empty space feels. The ship is not entering a denser region. It is making the same region more dangerous by moving through it at greater speed. From the ship's point of view, particles ahead arrive faster, harder, and more energetically. The outside universe becomes a flow aimed at the spacecraft's front. The darkness ahead is no longer passive. It becomes something the ship must survive. That is why shielding becomes one of the main limits on human speed. An engine can push the ship forward, but the shield must make sure the ship still exists after being pushed. At high speed, propulsion and protection are inseparable. There is no point building an engine that can reach a huge fraction of light speed if the spacecraft is damaged beyond survival before it arrives. A fast human ship might need a thick forward shield made of layers that can absorb and spread out impacts. It might need a long structure, with the crew habitat placed far behind the most exposed front surface. It might need replaceable plates or protective layers that can survive years of damage. But every shield adds mass, and every added mass makes the ship harder to accelerate. This is one of the cruelest parts of fast human travel. The ship becomes slower because it is trying not to die. Every protective layer that makes the mission safer also asks the engine for more work. Every kilogram saved makes acceleration easier, but may also remove something the crew needed to survive. The final design would be a compromise between courage and caution. This is why the fastest theoretical speed and the fastest survivable speed may be very different. A tiny probe can take more risk. It can be built with minimal shielding because losing one probe may be acceptable if many are launched. But a human ship cannot be treated like that. It must be protected with far more seriousness. Humans do not survive as disposable instruments. They survive inside mass. Air, water, food, medical equipment, radiation shelters, repair systems, spare parts, and living space all become part of the vehicle. Then, shielding must be added around that. Then, propulsion must push all of it. The faster the mission, the more every kilogram matters. Interstellar dust is only part of the threat. Gas matters too. The space between stars contains atoms, especially hydrogen. At low speeds, this thin gas is almost invisible to the mission. At extreme speeds, atoms ahead can strike the spacecraft like high-energy particles. They can heat the front of the ship, damage surfaces, and create secondary radiation when they hit shielding. This means the front of the spacecraft may become a place where the journey is constantly being paid for, particle by particle, impact by impact, heat by heat, radiation by radiation. The ship would have to survive not just one dramatic event, but a long accumulation of tiny events over years. A single particle may not destroy the mission, but billions of interactions can wear down material. That kind of danger is hard to picture because it is not cinematic. There may be no single flash that explains the failure. Instead, the front of the ship slowly becomes a record of the journey, scarred, heated, eroded, and stressed by countless encounters with matter so thin it would seem invisible at lower speed. The ship is not only traveling through space, it is being sanded by the universe. That is a very different kind of danger from a movie explosion. It is slower, quieter, more relentless. Navigation becomes part of survival too. A high-speed starship cannot simply aim, generally toward a star, and hope. It must know the environment ahead as well as possible, choose a path through regions with less dust, and avoid known clouds or dense areas. But interstellar space is not mapped with perfect detail. There will always be uncertainty. And uncertainty is dangerous when speed is extreme. The faster the ship travels, the less forgiving the path becomes. A small navigational mistake can grow into a large miss over interstellar distance. A region that looked empty from far away may contain more dust than expected. A hazard that would be manageable at lower speed may become mission-threatening at relativistic speed. High-speed travel makes prediction one of the most important forms of protection. The fastest route may not be the shortest route. The safest path may bend around danger. Radiation creates another problem. Space already contains radiation hazards for astronauts, but high-speed travel can make them worse. The ship's motion changes the energy of incoming particles and light from the forward direction. The faster the ship travels, the more the forward universe becomes compressed into a harsher environment. For the crew, that means the safest place may be deep behind layers of protection. The ship may not have a beautiful front window facing the stars. A real high-speed human craft might be built like a bunker, moving through space. The crew habitat could be buried behind shielding, water tanks, fuel, equipment, and structure. The forward view might be electronic, reconstructed from sensors rather than seen directly through glass. At a major fraction of light speed, a window facing forward may not be romantic. It may be a weakness. Heat is another quiet danger. Every impact deposits energy. Every shield absorbs some of it. Every engine produces waste heat. In space, heat cannot be carried away by air. It must be radiated away, which may require large radiators and careful thermal design. This means speed is also a thermal problem. Going fast creates energy. Energy becomes heat. Heat must go somewhere. If it cannot, the ship dies. This is why high-speed human travel is so much harder than simply asking for a faster engine. A faster engine may be possible in theory. A survivable fast ship is something else. A starship that arrives broken has not succeeded. A crew that arrives dead has not explored. That is why going too fast could kill you. In many ways, it could kill through impacts, radiation, heat, failed shielding, impossible braking, or the simple fact that small errors become unforgiving. The spacecraft must carry its own answers. This is why a practical human speed limit may appear long before physics says impossible. Not because light speed is reached, not because the engine cannot produce any more thrust, but because the ship becomes too massive, too dangerous, too expensive, or too hard to protect. That speed may be the real human limit. A limit made not only of physics, but of engineering judgment. Humans bring meaning to exploration, but they also bring limits. That does not make human travel hopeless. It makes it serious. A future crewed starship may travel far faster than anything today, perhaps at a meaningful fraction of light speed, while still choosing a speed below the extreme limit. It may not aim for the fastest number possible. It may aim for the fastest number that allows the ship to survive, slow down, and continue functioning. That is a very different kind of ambition. Not maximum speed, maximum survivable speed. In the end, going too fast could kill you, because speed changes the entire relationship between the ship and the universe. Dust becomes impact, gas becomes radiation, light shifts. Heat builds, navigation tightens, braking becomes harder. Every mistake grows more expensive. The empty space ahead becomes something the spacecraft must fight for every second of the journey. And that brings us to the final question. If chemical rockets are too slow, nuclear propulsion is only a bridge. Fusion is brutally difficult. Antimatter is dangerously extreme. Laser sails may be better for tiny probes. Time dilation separates the crew from Earth, and high-speed space itself can become lethal. Then what is the true speed limit of humanity? Not the speed limit of light, not the speed limit of imagination, but the speed limit of real humans, inside real ships, trying to survive the universe. That is the final question. After every engine, every idea, and every danger, the answer is not as simple as one number. It would be easy to say that the fastest humans could ever travel is just below the speed of light, because massive objects cannot reach light speed itself. But that answer would miss the most important part of the story. Humans do not travel as points of mass in an equation. Humans travel inside machines, and those machines must survive. A particle can move near the speed of light. Light itself moves at the speed of light. A tiny probe may one day be pushed to a large fraction of that speed by a laser sail. But a human spacecraft is different. It is not only a vehicle, it is a protected environment, a life support system, a shield, a home, an engine, and a promise that fragile bodies will still be alive when the journey ends. So the real human speed limit is not only written in relativity, it is written in survival. Every chapter of this journey has shown the same pattern from a different direction. Chemical rockets gave us power, but not enough energy. Nuclear propulsion gave us a deeper source of power, but not a full answer to the stars. Fusion made interstellar speed easier to imagine, while also showing how difficult it would be to control a star-like process inside a ship. Antimatter offered even greater energy, but with dangers so extreme that the fuel itself becomes part of the threat. Laser sails showed that tiny machines may move fastest because they avoid carrying most of the mass humans need. All of this points to one answer. The fastest humans could ever travel is probably not the fastest speed allowed by physics. It is the fastest speed that can be reached, survived, controlled, and slowed down from. That last part matters more than it seems. Reaching speed is only one moment in the story. A real human journey must also live at that speed, navigate at that speed, communicate across distance, protect the crew, and eventually arrive. The ship has to turn velocity into a completed mission. A maximum speed that only works for a brief flyby or only works if the crew does not survive is not the answer we are looking for. That may sound less dramatic than saying 99% of the speed of light, but it is more realistic. A number is not enough. A human mission needs acceleration that bodies can tolerate, shielding that can survive the journey, engines that can run for years, navigation that can avoid hazards, and a way to arrive safely. A ship that cannot stop is not really traveling. It is only passing through. A ship that cannot protect its crew is not exploration. It is sacrifice. So the true speed limit of humanity may be a zone, not a single point. Below that zone, we are too slow for the stars to fit inside human lives. Inside that zone, the nearest stars become brutally difficult but imaginable. Above that zone, the energy, shielding, braking, and survival problems may become too extreme for humans to be the best passengers. Machines may go first. That may be the future we should expect. Before humans cross the distance between stars, machines may map the safest routes, measure the dust between systems, test laser sails, and prove that high-speed interstellar travel can work at all. They may become the first fast travelers because they can be light, silent, and expendable. They can take the risks that life cannot take. Tiny probes may travel faster than any crewed ship for a long time. They may be pushed by lasers, accelerated violently, sent on flybys, and allowed to risk failure. They can be small and replaceable in a way humans never are. If one probe is lost, another can be sent. If one probe is damaged, no one dies. Humans bring meaning, but they also bring requirements. This is why the first interstellar age may be robotic before it is human. Small probes could cross to nearby stars at speeds that would be too dangerous or impractical for people. They could return faint images, measure dust, study planets, and tell us what is waiting beyond the solar system. They would be our eyes, moving faster than our bodies can follow. A crewed starship, if it ever comes, may be slower and heavier. It may not be designed to break every speed record. It may be designed to arrive. It may choose the highest speed that still leaves room for shielding, braking, repair, and life. That is a very different kind of ambition. Not maximum speed. Maximum survivable speed. This may sound less exciting, but it is actually the more powerful idea. A civilization that understands maximum survivable speed is no longer just chasing numbers. It is learning how to carry life through hostile conditions without pretending those conditions do not exist. It is treating the universe seriously, and perhaps that is what makes true interstellar travel possible. Not ignoring danger, but designing around it. The faster humans go, the more the mission becomes a battle against energy, mass, heat, radiation, dust, braking, and time. This is why the speed of light remains such a powerful boundary. It is not just that humans cannot reach it. It is that every attempt to approach it makes the universe more demanding. Energy costs rise. Time changes. The forward environment becomes harsher. The ship becomes harder to protect. The final steps toward light speed are not like simply pressing harder on an accelerator. They are a climb into more extreme physics. So perhaps the most honest answer is this. Humans may one day travel at a meaningful fraction of light speed, but probably not light speed itself. And the exact fraction will be decided less by dreams than by survival. At 10% of light speed, the nearest stars become reachable in decades, not tens of thousands of years. That does not make the journey easy, but it makes it emotionally possible. It turns the nearest stars from unreachable lights into destinations that a civilization could plan for. That may be the first great threshold. Not reaching light speed, reaching a speed where the stars become part of the human future. For a long time, the stars have been places of imagination, more than destination. We can measure them, photograph them, and study the planets around some of them. but they remain separated from us by time. A meaningful fraction of light speed would change that relationship. The nearest stars would still be far away, but they would no longer feel completely outside the reach of a future civilization. Light does not need a ship. Light does not need air. Light does not need shielding. Light does not need to slow down and build a home when it arrives. Humans do. That is why the universe is both open and closed at the same time. It allows us to imagine crossing interstellar distances with engines, sails, fusion, antimatter, and relativistic travel below light speed. But it does not make any of it easy. It demands payment for every gain in speed, and the payment is always made in energy, risk, and time. This is the quiet truth behind all deep space speed. The universe is not blocking humanity with a single locked door. It is presenting a series of doors, each harder to open than the last. Leaving Earth was one door, reaching the Moon was another. Reaching Mars with humans will be another. Moving through the outer solar system will be another. Interstellar travel will be a door so heavy that it may take centuries to open. And if such a ship ever leaves the solar system, it may not look like the bright silver starships of imagination. It may look heavy, shielded, dark, and strange. Its crew may live deep inside it, behind layers of water, metal, fuel, and radiation protection. Its front may be armored against particles too small to see. That is what the fastest human spacecraft might really be. Not a machine that ignores the universe. A machine that respects it enough to survive. In the end, the question is not only how fast humans could ever travel in space, it is what kind of civilization would be needed to make that speed meaningful. A civilization that can build powerful engines, strong shields, stable habitats, and crews prepared for the cost of leaving Earth behind, perhaps not only in space, but in time. At low speed, a journey is a mission. At interstellar speed, a journey becomes a life. At relativistic speed, a journey may become a departure from the present itself. That is why the fastest humans could ever travel will not simply be decided by engines. It will be decided by the full weight of what humans are willing to build, risk, and lose. We may one day push probes toward nearby stars and eventually build crewed ships that move at fractions of light speed. But every step will force the same question again. Can we survive the speed we create? If the answer is yes, then the stars become closer. If the answer is no, then speed becomes just another way to fail. So the final answer is calm, but enormous. The fastest humans could ever travel in space is probably somewhere below light speed, perhaps at meaningful fractions of it, if future technology becomes advanced enough. But the real limit is not only physics. It is the point where energy, shielding, time dilation, dust impacts, heat, braking, and human survival all meet. That is the speed limit of humanity. Not the fastest speed the universe allows, but the fastest speed life can carry with it. And maybe, one day, a ship will leave the solar system at a speed that would seem impossible to us now. The sun will shrink behind it. The planets will become memories. The stars ahead will no longer be only lights in the sky, but places waiting across the dark. They will not be breaking the universe. They will be learning how far the universe allows life to go. That is a more grounded kind of wonder. The goal is not to cheat physics or escape reality. The goal is to understand the rules deeply enough to move within them. If humans ever travel at a meaningful fraction of light speed, it will not be because the universe became easy. It will be because civilization became patient, careful, and powerful enough to survive the difficulty. And that may be the real meaning of speed in space, not escape from the laws of physics, but the deepest test of whether humans can live within them and still reach the stars. Thank you for watching this journey through the fastest humans could ever travel in space. If you enjoyed this calm exploration of deep space, subscribe to the channel for more space documentaries like this. Leave a like if you want more slow journeys through the mysteries of the cosmos, and write in the comments what impossible question you want to explore next. Tonight, you are watching the Just About Space channel, talking about what is the fastest humans could ever travel in space. Sleep well and keep looking up. Good night.